We are starting and ending our semester with chapter 7 on system of equations and inequalities. We are going to cover only 3 sections. We will learn about system of linear equations with 2 variables, the system of linear equations in 3 variables, and we'll consider some nonlinear equations and inequalities with 2 variables. Section 1, let's look at 2 variable linear equations. In this section, we are going to learn how to solve system of equations by graphing, system of equations by substitution, by additions, and how to identify inconsistent system of equations containing 2 variables. We will also learn how to express the solution of a system of dependent equations containing 2 variables. There are 3 types of system of linear equations in 2 variables and 3 types of solution. So, an independent system has exactly one solution, a pair xy. The point where the 2 lines intersect on a graph is the solution. An inconsistent system has no solution. In this case, the 2 lines are parallel, so will never meet. We also have dependent system that has infinitely many solutions. In this case, the lines coincide. They are the same line, so every coordinate pair on the line is a solution to both equations. The 3 figures below represent the 3 cases. On the first one, we have independent systems with exactly one solution. The second case, inconsistent system with 2 parallel lines. And the last one is dependent solution in which both lines coincides. Example, we want to learn how to determine the solution of 2 equations. Here we may substitute the order paired 5, 1 into both equations to determine if it is actually a solution to the equation. In doing so, we realize that the equation remains true because 8 equals to 8 and 1 equals to 1. So the order paired 5, 1 is a solution to the equation. If we know that these equations are not the same, then it is the unique solution because they are independent equations. So we can look at the graph here of 2 equations, 2x plus y equals to minus 8 and x minus y equals to minus 1. So we use substitution, we will solve the first equation for y. So we solve the first equation for y in terms of x, and we will have y equals to negative 2x minus 8, and then replace it in the second equation. And then as we replace it, we have x minus y equals to minus 1, so y equals to x plus 1. So the graphs are there, and we can see graphically that the solutions are at x equals to minus 3 and y equals to minus 2, the unique solution. So we can check these solutions by replacing the values into the equation. And for the first equation, we will get minus 8 equals to minus 8. The second equation, minus 1 equals to minus 1. So the 2 equations remain true for the point negative 2, 3, negative 2. We can also solve an equation using substitution. This is the procedure. You solve one of the 2 equations for one of the variables in terms of the order, then substitute the expression of the solution in the first equation into the second equation. Substitute that solution into either of the original equation to find the value of the first variable. If possible, write the solution as an ordered pair. Then check the solution in both equations. So you take one of the variable as a constant and solve as if it was just one equation of one variable. Now the solution you have, you replace it in the other equation and solve for the unknown, and then go back to the original substitution to get the solution of the variable that you kept as a constant. Example, we want to solve the system of equation minus x plus y equals to minus 5 and 2x minus 5y equals to 1. So first, we will solve the first equation for y, that is keeping x as a constant. We have that y equals to x minus 5. Then we are going to substitute that into the second equation. 2x minus 5y equals to 1. So we substitute y by x minus 5, and we will end up having 2x minus 5x plus 25 equals to 1. That is minus 3x equals to minus 24. So x equals to 8. Now we replace the value of x into the equation to find y equals to minus 8 plus y equals to minus 5, which gives y equals to 3. So the solution to the system of equation is 8, 3. We can also solve a system of equation in two variables by addition. In this method, we will try to eliminate one of the variables by multiplying both equations by appropriate constant that will make the variables we want to eliminate to have the same coefficient. For example, we have two equations. X plus 2y equals to minus 1 and minus x plus y equals to 3. In this case, the variable x have opposite, almost the same coefficient, just that they are of opposite sign. So we can add the two equations to get an equation with a single variable y. So when we add both equations, x plus 2y minus x plus y, we have 3y equals to 2. So y equals to 2 over 3 is the value for y that we will replace in any of the two equations. Like in the first equation, we will have, we will choose we solve for x, choose the second equation. You can choose the first or the second, and replace the value of y by 2 over 3. So we have minus x plus y equals to 3. That is minus x plus 3 over 2 plus 2 over 3 equals to 3. So x equals to minus 7 over 3. So the solution to this equation is x equals to minus 7 over 3, y equals to 2 over 3. So if it's happened that none of the coefficient has the same value, we look at the equations and we will determine how we can eliminate one of the variables. For example, if we want to eliminate x, we will multiply the second equation by minus 3 so that we can have minus 3x on the second equation, and while adding, we will eliminate x. If we want to eliminate y, we look at the coefficients of y in both equations and reverse them in multiplying each of the equations. Like we will multiply the first equation by 2, and then the second equation by 5. So you reverse the coefficients of the equation while doing the multiplication in order to eliminate a variable. So by doing so, if we want to eliminate x, in this case, we will multiply the second equation by minus 3, and we will eliminate x and get 11y equals to minus 44. So y equals to minus 4. Now that we have the value of y, we can replace it in any of the two equations of the system. If we replace it on the equation 3x plus 5y equals to minus 11, we will have 3x plus 4 plus 5 times minus 4 equals to minus 11. So 3x minus 20 equals to minus 11. 3x equals to 9, so x equals to 3. So our solution is 3 minus 4. So on the right side, you have the graph of that equation. How do we identify inconsistent solution? To identify inconsistent solution, we can write both equations in the same form. If we're writing the equation as a standard equation of a line, we write both equations as y equals to, and then we will see that they are exactly the same equation. Or we may decide to solve for one variable, use any of the methods we have, will lead us to get an inconsistency. For example, let's say that we want to, we have the equation x plus 2y equals to 13 is the second equation. So from the first one, we have x equals to 9 minus 2y. So we will replace that in the second equation to have 9 minus 2y plus 2y equals to 13, meaning that 9 equals to 13, which is impossible. So to get to this impossibility, we can either solve for one variable. We can use addition as well. Any algebraic operation we can make will lead us to an impossibility. So to express equation as dependent equations, we may either solve again for one variable and see that on the other variable, or the best way is to try to, as I say in the previous slide, we try to express the equation in standard form and we see that there is an inconsistency. Because solving for one variable will lead to a number that is different from another one being expressed as equal to. Now, to detect dependency, express the equations in standard form and see if you are going to have the same equation. For example, here we can write that x equals to 2 minus 3y for the first equation. And on the second equation, you have 3x equals to 6 minus 9y, divide through by 3. You will also have x equals to 2 minus 3y. So with the addition method, we want to eliminate one of the variables by adding the equation. In this case, we'll focus on eliminating x. By eliminating x on the first equation, we are going to have x equals to 2 minus 3y. And then we replace it on the first equation. Or in doing the natural elimination, we multiply the second equation by minus 3. And we will have minus 3, the first equation by minus 3, we'll have minus 3 minus 6 minus 9y equals to minus 6. So adding both equations give us 0 equals to 0. But another way is to just observe that by multiplying let's go back to the equation, x plus 3y equals to 2. If we multiply the first equation by 3, we will have 3x plus 9y equals to 6, which is the same equation as the second one. We can have a system of equation with more than 2 variables. We will look at an example of a system of equation with 3 variables here. So in this, we are going to learn how to solve a system of 3 equations in 3 variables, identify inconsistent system of equation containing 3 variables, and express the solution of a system of dependent equation containing 3 variables. Just as for 2 variables, we have 3 cases. First case is when we have a unique solution. Second case is when we have no solution. Third case is when we have an infinite number of solutions. Example, determine whether the ordered triple 3 minus 2, 1 is a solution to the system. We have the system of equation and we will replace the value of x by 3, y by negative 2, and z by 1. In doing so, we will realize that the point 3 minus 2 and 1 is actually a solution to the equation. So when you observe that the point is a solution, it can just be one of an infinite number of solutions. You will take that as a solution only if you know that the equations are not dependent. and there is one solution. If the equations are independent equations with exactly with a solution that is known, that solution is unique. But if you have not checked if the system is independent, you cannot just conclude because one of a given point is a solution that it is the unique solution. So when we are given a system of equation with three variables, we may decide to pick any pair of equation and solve for one variable, just as if you are taking the other two variables as constants. So you can take, for x, you can solve for x in two equations and then replace it in the other equation. So pick another pair of equation and solve for the same variable. You have created a system of two equations in two unknown. Solve the resulting 2 by 2 system. So back substitute non-variable into any of the original equations to solve for the missing variable. Example, solve the equation x minus 2y plus 3z equals to 9, minus x plus 3y minus z equals to minus 6, 2x minus 5y plus 5z equals to 17. There will always be several choices as to where to begin, but the most obvious first step here is to eliminate x by adding equation 1 and 2. By adding equation 1 and 2, we eliminate x and we get one variable. We get an equation with two variables, y plus 2z equals to 3. Next, we can observe that we can eliminate x again in equation 1 and 2 by multiplying equation 1 by minus 2, and then get another equation of y and z, which is minus y minus z equals to minus 1. That is y plus z equals to 1. Now we have two systems of equation 3 and equation 5. Sorry, equation 4 and equation 5. I put it here as 3. Anyway. So we have y plus 2z equals to 3 and minus y minus z equals to minus 1. If we add these two equations, we are going to get z equals to 2. And we can solve z equals to 2 that we can replace into the second equation, y plus 2z equals to 3 to get y plus 4 equals to 3. So y equals to negative 1. Now we have a value of x, a value of z and y that we replace on the first equation to get a value for x. So that's using substitution. So the solution is x equals to 1, y equals to negative 1, and z equals to 2. How do we identify inconsistent equations? Let's use an example. In this example, we have three systems. We will decide to eliminate x in equation 1 and 2 to get another equation, minus y minus 4z equals to 7. Next, we want to eliminate x by using equation 3 and either 1 or 2. So in this case, we are going to multiply equation 1 by minus 5 to get minus 5x plus 15y minus 5z equals to minus 20. Then we add it to equation 3. We add it to equation 3 to get a new equation, minus x plus 2y minus 5z equals to 3. So if we look at the coefficient of x, we can add it up here. You get first and second equation. We are repeating that. First and second equation give us minus y minus 4z. Next, we multiply equation 1 by minus 5 and add it to equation 3. And we will get 2y plus 8z equals to minus 12. Then we multiply equation 4 by 2 and add it to equation 5 to get minus 2y minus 8z equal to 14. And then 2y plus 8z equal to minus 14. When we add the two numbers, we get 0 equals to 2, which is inconsistent. So how to express a system of equation with three variables as dependent variables? Let's use an example again here. Everything is done like we did for two unknown variables. So first we can multiply equation 1 by minus 2 and add it to equation 2. And we will get 0 equals to 0. So both equations are identical, as you can see. When the system is dependent, we can find general expression for the solution. Adding equation 1 and equation 3, we have 2x plus y minus 3z equals to 0. So x minus y plus z equals to 0. And then we have 3x minus 2z equals to 0. We then solve the resulting equation for z, and we have z equals to 3 over 2x. In this case, we will express all the solutions as a function of z. We back substitute the expression for z into one of the equations and solve for y. So we have y equals to 5 over 2x. So the solution set is x, 5 over 2x, and 3 over 2x. In 7.3, we are going to look at system of nonlinear equations and inequalities with two variables. In this section, we will solve a system of nonlinear equation using substitution, a system of nonlinear equation using elimination, graph a nonlinear inequality, and a system of nonlinear inequality. So there are three possible types of solution for a system of nonlinear equations involving a parabola and a line. So if we have two equations, one is a line, the other one is a parabola, there might be no solution. That means parabola and the line does not intersect. There could be one solution, meaning that they intersect exactly at one point. And there could be two solutions, meaning that they could intersect at exactly 2 points. So either there is no solution, one solution, or two solutions if we want to intersect a parabola with a line. So these are the possibilities using a graph. The first case, there is no solution. The two graphs are not meeting. In the second case, the two graphs meet exactly at one point. We will learn later that this is the tangent to the line, to the graph, when a line intersects a graph at exactly 1 point. And the third graph is when there is exactly two solutions. In this case, the line and the parabola intersect at 2 points. So to solve a system of equation containing a line and a parabola, we solve the linear equation for one of the variables and then substitute it into the parabola or the quadratic equation and solve the quadratic equation, then go back to the line equation to get the variables that was considered a constant. Then we check the solutions. Example, we have a system of equations here. The first one is a line, x minus y equals to minus 1. And the second one is a quadratic expression, y equals to x squared plus 1. So solving the first equation for y will give us x equals to y minus 1, which we can replace in the second equation and have y equals to x squared is now y minus 1 squared plus 1. And then in solving this, we get to the quadratic expression y squared minus 3y plus 2, which is equal to y minus 2 times y minus 1 equals to 0, as we know how to solve a quadratic equation, y equals to 1 or y equals to 2. we have the value of y. For each of the values of y, we will get a value for x. So we'll have first x minus 1 equals to minus 1, and x equals to 0. And the other solution is replacing y by 2, and we'll have x minus 2 equals to minus 1. That is x equals to 2 minus 1, which is 1. So the solution are 1, 2, and 0, 1. So the graph of these two functions are here, two equations, and we can see the 2 points where the line intercepts the parabola. So we can also intersect a line with a circle. Either there is no solution, that is the line does not intersect the circle. Exactly one solution, that means the line intersects the circle at exactly 1 point, or two solutions. Example, we have two equations here. The first is the circle x squared plus y squared equals to 5. And the second is the line y equals to 3x minus 5. So we may just replace the value of y into the equation and get x squared plus 3x minus 5 squared equals to 5. And expanding this will lead us to 10x squared minus 30x plus 20 equals to 0. So we can factor this to get 10 times x minus 2 times x minus 1 equals to 0. That is x equals to 2 or x equals to 1. So we have two values of x. We are going to replace it into the circle. To the equation of the line. And for each value of x, we are going to get a value for y. So y equals to 3 times 2 minus 5 equals to 1, or y equals to 3 times 1 minus 5 equals to minus 2. So we have the 2 points, 2, 1, and 1 minus 2. We may solve a system of nonlinear equation representing a circle and an ellipse. So to solve this equation, we begin by eliminating x squared, because we will consider it as two equations. We will consider it as two equations and take the square as single values and then solve for those squares to get the actual values of x and y. So we eliminate x squared first by multiplying the first equation by minus 3 and add it to the second equation to get 22 y squared equals to 22. That is y squared equals to 1 and y equals to plus or negative 1, which we will replace into the first equation to have x squared equals to 25. That is x equals to plus or minus 5. So that gives us 4 possible solutions. When x equals to 5 and y equals to 1, when x equals to minus 5 and y equals to 1, then when x equals to 5 and y equals to negative 1, and when x equals to minus 5 and y equals to minus 1. In this case, we have 4 solutions. Graphing a nonlinear inequality. If we are given an inequality bounded by a parabola, we can sketch the graph. Graph the parabola as if it were an equation. This is the boundary for the region, that is the solution set. If the boundary is included in the region, that is we have less than or equals to or greater than or equals to, then the parabola is graphed as a solid line. If the boundary is not, that is in the case of less than or greater than, the parabola will be graphed as a dashed line. Then test a point in one of the regions to determine whether it satisfies the inequality statement. If the statement is true, the solution set is the region including the point. If the statement is false, the solution set is the region on the other side of the boundary line. Then we shade the region representing the solution. Example, solve the parabola graph. Solve an inequality for a parabola graph. Y is greater than x squared plus 1. So here is greater than. So the parabola will be a dash in dashed line. Now we will consider the equation of the quadratic equation y equal to x squared plus 1. We will make the graph for that equation and identify a point either within the equation, the parabola, or outside the parabola. Let's look at the graph to understand what I mean. So this is the parabola, and we can pick a point. It's always good to take the origin, for example. If we take the origin in this equation, in the example we took the point 0,2, but I want to take the origin. When the origin is clearly not on the parabola, it's good to always take the origin. So let's take the origin into the equation. Does the origin satisfy this equation? Can we say 0 is greater than 0 plus 1? 0 is not greater than 1, so the origin is not part of the solution. We go back to the equation. The origin, which is 0, 0, is not part of the solution. So the region that does not contain the origin, which is the inner region, which is shaded here, is the solution to the inequality. So solutions to the inequality are obtained by observing the regions that are expressed in the graph. Pick an easy point of the plane and then test it in the inequalities and realize where that point is, observe where that point is to determine where the solution is. Either the point is in the solution or it is not. So graphing a system of nonlinear inequalities is exactly the same thing we are going to do. Now we will draw the graph of each of the inequality and identify a point of the region and use those points to determine what region actually is solution to the system of inequality. So we pick a point in each of the region as they are partitioned on the plane. We pick a point, test that point into the system of inequality. If that point does not satisfy any of the system, the region where that point is coming from is not part of the solution. So consider this, the inequality x squared minus y is less than or equals to 0, and 2x squared plus y is less than or equals to 12. So these are two equations. These two equations are clearly parabola. We can find the point of intersection by elimination process. Add both equation and the variable y will be eliminated, then we solve for x. We will have x squared minus y equals to 0. Fix this. We have x squared minus y equals to 0, so 2x squared plus y equals to 0 is the second equation. Push it here. Okay. So by adding the two equations, we will have 3x squared equals to 12, so x squared equals to 4, and x equals to plus or minus 2. Those are the point of intersection of the two parabola. So if we substitute the x value in one of the equation and solve for y, we are going to have x squared minus y equals to 0, so 4 minus y equals to 0, so y equals to 4. The 2 points of intersection are 2, 4 and minus 2, 4. Notice that the equation can be rewritten as follows. We can write the equation as x squared minus y is less than or equals to 0 and x squared is less than or equals to y. So x is greater than or equals to x squared. 2x squared plus y is less than or equals to 12, so x is less than minus 12, x squared plus 12. Essentially, what you will do, you can graph both equations, and then you will see that we can determine the region that satisfied all the, where all solutions, we can partition the parabola, we can partition the plane in several regions and test a point from each of the regions. So we can see that if we pick a point like x equals to 0 and y equals to 2, x equals to 0, we will get 0 here, y equals to 2, 2 is less than or equals to 12. X equals to 0, y equals to 2, minus 2 is less than or equals to 0. So this point, the point 0, 2, which is here, is a solution to the inequality. So the region enclosed by that region, but the region containing that point is the solution to the inequality. So always pick an easy point after you have graphed your equations to determine the region which is actually the solution of the inequality. Okay, this is the end of the course for this semester. Your exam is available. You can take it before the 19th of August. I advise you to take it before Sunday. That's the reason why we are ending the chapter so early, so that you can be able to take your exam before Sunday, but you have until Wednesday to take the exam. I wish you all the best. If you have any question, don't hesitate to contact me.